All right, so in this video, we're going to take a look and we're going to jump into chapter 2, where we're going to take a look at atoms. And eventually, we're going to see and relate some of the characteristics here to probably the most important tool that we use in chemistry, which is the periodic table. So our book is called Chemistry Atoms First, and that is by intent because what we're doing in our class is we're going to start small and then sort of build complexity onto that. In other chemistry classes, they do it in the other direction, starting big and then going down to the small level. We're doing it in hopefully a way that makes sense. So we're going to take a look at atoms. We will see what atoms are made up of. We'll take a look at some of the experiments that help us figure out what the components of an atom are, and then we'll take a look at the notation of how we represent those different components. And finally, we'll take a look at the periodic table, see how we can interpret it, how we can find things on the periodic table, and then we will look at some calculations involving some of the concepts we would have introduced before. So, what exactly is an atom to begin with? Well, we can define an atom as simply the smallest quantity of matter that still has the characteristics of that particular sample of matter. Now, to give us a little perspective, if we go back to how we defined matter early on in the earlier weeks, we said that matter generally comes in two categories. We have mixtures and we have pure substances, right? We talked about mixtures, what they actually are, homogeneous versus heterogeneous. And then on the pure substances, we have two subcategories. We have elements and we have compounds. And the difference between them stems from the atoms that make up these two categories. So in an element, we have only one type of atom present. So for example, if you have a sample of gold, which has a symbol AU, that would be an element because that sample only contains gold atoms. Similarly, if you have a sample of oxygen in a gas canister, for example, that oxygen is made up of is O2, that's oxygen that you breathe in, for example, and that's still only made up of one type of atom. There's only O oxygen atoms present in there. So when we talk about atoms, and they make up things like elements and compounds. In the case of compounds, you have different elements that are combined in a fixed ratio. Like in water, you have two hydrogen atoms and one oxygen atom. In the case of elements, these are just made up of one type of atom. So an elements, again, it's just something that cannot be broken down into two or more simpler substances by any means. So again, elements here made up of one type of atom. If you look at a sample of gold, for example, this would be composed of only gold atoms. If you could zoom in on it with a really, really powerful microscope, you would be able to see those gold atoms present. Now, there were lots of experiments that were done early on, a couple of hundred years ago, when people were trying to decide and think about, well, all this stuff around us and in us, what actually make up? What are the things that make up the stuff around us? And John Dalton, who was probably one of the earliest scientists to try to approach that question in a scientific method, proposed what's known as the atomic theory. And part of that atomic theory says that atoms, of which all matter consists, are tiny, indivisible particles. And that's just part of 4 or 5 tenets of his atomic theory called Dalton's atomic theory. So according to him, then, these atoms are tiny, they make up everything around us, and they're indivisible, meaning we cannot break them down further. However, since Dalton, we have since known that the atom can, in fact, be broken down into smaller pieces that are known as subatomic particles. Okay, so I'm going to say ... has since been dated. And these subatomic particles are very, very important, and they explain a lot of the behavior of the matter around us. So the nature of these subatomic particles, how many we have, how they are arranged, will determine all of the characteristics, both chemical and physical properties of the atoms. And again, atoms making up everything around us, those subatomic particles will then determine the properties of all things around us, in us, etc. So this is sort of the backdrop of what we're going to be exploring in this section here. We will start by examining the structure of the atoms, and then what the atoms are actually made up of, these tiny subatomic particles that are key to the behavior of atoms. So let's take a look now at some of the earliest experiments that helped us figure out. So experiments that led to the discovery of some of these subatomic particles. So we're not going to talk about all of them, but some of them are particularly important. So again, going back a couple hundred years now, late 1800s, early 1900s, they were doing research involving radiation. So radiation is just the emission or the giving off and the transmission of energy in the form of waves. Okay, we'll talk more about waves in the subsequent chapters. And what they commonly used was something called a cathode ray tube, which is often abbreviated CRT. And this is the forerunner, if you can imagine back, 20, 30 years, to things like these old TVs. You remember old TVs? They didn't all used to be flat screens. They used to be huge hulking things, and they were actually cathode rays. So old TVs and also old computers, old computer monitors, all right, they have their basis in these cathode ray tubes. And the way that they work is actually very, very simple. So you have here a big glass tube, essentially, and most of the air has been taken out or evacuated from this tube. So this is the tube that we have here. On one side of the tube, you have two metal plates, or two plates in general. There's one plate, and there is another plate. And what they found is that when those plates are connected to a high voltage, okay, so these are the leads here. What they found was that one of these plates, this plate, for instance, down here, which is called a cathode, emits an invisible or gives off an invisible ray. And that invisible ray, how do we know that it's invisible? Well, when it actually strikes the other side of the cathode ray tube, if that surface there is coated in phosphor, what happens is it actually glows. It produces a very bright light. So they were able to observe this, and what they also found was that ray, a cathode ray, emanated from the negatively charged cathode and went through the positively charged anode. What they discovered was that it didn't matter what the cathode and anode were made up of. So the identity of the cathode and anode was irrelevant. So whether they used one particular metal or a different one for the cathode and anode, they would always see this occurring. And that's very important because what it told them was that these rays actually came out of pretty much all different types of matter. So it was common to lots of different things, right? They were found in pretty much all things. What they also noticed was that when these cathode rays were subjected to either an electric field, so we have an electric field down here, or a magnetic field using the north and south magnet, they were actually deflected by both of those. And that's a very important observation because it led to some of the characteristics of this particular cathode ray and what actually made up what that cathode ray was composed of. So the cathode rays being deflected by both an electric and a magnetic field was important because what they found was that the rays, if they came, they were actually repelled by the negative electrode in the electric field, and they were attracted to the positive electrode in that electric field. So what that told them was that these rays, whatever they were actually composed of particles. And because they were attracted to the positive electrode in that field, that means that they had a charge, which was a negative charge. Okay, they were repelled from the negative electrode. They were attracted towards the positive electrode. So they're negatively charged particles that they discovered with this seemingly simple type experiment. So another scientist here that was able to deduce this was J.J. Thomson, middle 1900s, was able to note that deflection of those cathode rays by being repelled by the negative plate, being attracted to the positive plate. So that meant that these rays were actually had a charge associated with them, which was negative. And he proposed that these were actually made up of negatively charged particles. And he called these particles electrons. And electrons are central to our understanding of not just chemistry, but all fields of science to this day. Now, he was able, by changing that electric field, so consider the negative electrode up here, positive electrode down there. You can alter that electric field and then measure the deflection of the cathode rays that are going through that. He was able to do some calculations and was able to figure out what's known as the charge to mass ratio of electrons. And that ended up being 1.76 times 10 to the 8 C. And we saw that this abbreviation, the symbol early on briefly. This is the symbol for the electric charge called Coulomb. That's the SI unit for electric charge per gram. So what he found here was that per gram, a gram of electrons, for example, would have a charge of 1.76 times 10 to the 8 coulombs. And that's important because that helped scientists later on to actually figure out some other properties of electrons. So for instance, Millikan, again, late 1800s, early 1900s, also did an experiment to help figure out some of the characteristics of these electrons. He did an experiment called the oil drop experiment, where essentially you have this chamber here. There's this little device that had oil in it, some sample of oil. He was able to atomize that oil sample. And as the oil was turned into this fine mist, essentially in here, and it fell through from the top to the bottom, the oil particles themselves were able to pick up some sort of a static charge in the air. And then he could suspend these oil particles by varying this electric field. So depending on what charge these particles adopted by falling through here, he was able then to suspend by altering the magnetic field, he was able to suspend them in this device, in this oil drop experiment. Now, the key thing here that he discovered was that when when he determined the charge on any particular drop, any particular oil drop, so not all the drops are going to be the same size, what he actually found was that the charge on the drops, the oil drops, was always a multiple of a particular number. And that number was negative 1.6022 times 10 to the negative 19 coulombs. So what he deduced was that this then was the charge on a single electron. Okay, so J.J. Thomson early on with the cathode ray tube is able to figure out, well, there are these particles that are coming out of pretty much every single element there is. They have a negative charge associated with them. We're going to call those particles now electrons. With that experiment in millikan's, they were able to determine the charge on an electron. So again, 10 to the negative 19, very, very small. So this number was able to be used with the charge to mass ratio that Thomson discovered early on. And just by doing, a little bit of dimensional analysis on that, if you know what the charge on an electron is and you know what the charge to mass ratio is, we can simply divide those two. Your coulombs cancel out. You end up with 1 over 1 over gram. You evaluate that, you end up with grams as your unit. You evaluate everything else, and you end up with this number here. And that is, so they calculated then 9.10 times 10 to the negative 28 grams. That is the mass of an electron. Very, very, very small, but there's a mass associated with it. And that electron, again, as they found earlier, was coming out, it was emanating from pretty much every sample of matter they would put in that cathode ray tube. So it was present in everything. So other scientists at the time did other types of experiments that uh, helped us figure out some of the other characteristics of matter. So for example, Röntgen, again, around the same time, discovered X-rays, and he discovered those by pointing cathode rays either against a glass or a metal, and then that caused the emission of another type of rays that he called X-rays. And the interesting thing about X-rays is that these were not deflected by a magnetic or an electric field. So that means then that they did not have a charge associated with them, with these X-rays. Becquerel, also around the same time, discovered something known as radioactivity, which is just the spontaneous emission of radiation. And unlike X-rays, these were emitted spontaneously, right? So with X-rays, you have to actually, shine this cathode ray tube onto a glass or a metal, and then the X-rays are ejected. Whereas with radioactivity, the emission of this type of radiation was actually just spontaneous. It was just the inherent nature of that sample itself. So substances such as uranium, for instance, spontaneously emits these types of radiation, and there are 3 types of radiation that they were exploring early on. So what are these types of radiation then that could be produced? Well, there are 3 types of radiation that they observed. So we have the names along with the symbols for these. So they are alpha rays. So if you can imagine this this lead block here that contains a radioactive substance, a lead block is there to protect people around it, and then we can force the radiation then to go through just a confined path. And what they found was that alpha rays, so this is the symbol for alpha, these consist of positively charged particles called alpha particles. And they knew that it was positively charged because the alpha rays here were deflected towards the negative electrode, right? So opposites attract. So if something is being attracted towards the negative electrode, this should be positive. So alpha rays are positive, made up of alpha particles. By the same token, if it's being repelled by the positive electrode, that means it should also be positive, right? So like charges repel, opposite charges attract, right? That's the general gist of how charges work. So just based on the deflection, they were able to deduce the charge. Beta rays or beta particles, so this is the symbol for beta, kind of looks like a bee with a tail here at the front. These are essentially electrons. So electrons, we just said, are negatively charged. And these are deflected away from the negatively charged plate or towards the positive plate, right? And we see that up here, right? Your beta rays made up of beta particles. These are negative. They are attracted towards the positive plate. The third type of radiation is known as gamma rays. And gamma has the, rewrite that. The gamma has the symbol like this. And these are kind of similar to X-rays in the sense that they are not influenced by an electric field or a magnetic field for that matter. So they just go straight through. Okay, so these are gamma rays here. And they're all, by all intents and purposes, they're just energy, right? There's no particles associated with these gamma rays. We're going to come back to these types of radiation a little bit later on. So some other experiments and scientists that did a lot of groundbreaking work to help figure out these subatomic particles. Another person who was very influential in this was Ernest Rutherford, along with his associates Geiger and Marsden. They performed what's known as the gold foil experiment. And the idea behind this is also very simple. A lot of these experiments, they're not really complicated things. They're just really simple, but the observations that people make and then the conclusions that are drawn, those are kind of the groundbreaking stuff. So what Ernest Rutherford did is he used one of these sources of radiation, specifically these alpha particles, to help figure out the structure and the anatomy of an atom, right? So he's going to use these alpha particles, which again are positively charged. And what they did was they, in again, a lead box or something, they have a source of radiation that would give off these alpha particles coming out of this box here. So think of it like a stream of positive charges, and they would aim it at this gold foil. So a gold foil is exactly what it sounds like. It's a piece of foil that instead of being aluminum, for example, it's gold. And they would essentially aim the alpha particles at this gold foil. And based on the prevailing theory of the atom at the time, which is called the plum pudding model, put forward by our friend J.J. Thomson, we would expect that all of these positive particles to go right through the gold foil unimpeded, so go straight through. Now, what they actually noticed was that, yes, while the majority of the alpha particles went right through, occasionally they would see some deflections. So instead of going in a straight line, after hitting the gold foil, they would be deflected, by a certain angle. We'll call that theta, either one way or another way. And in some cases, that positive particle would actually be detected back in this direction. So it would come in, hit the gold foil, and then bounce right back where it came from. And that is absolutely not what they expected. They didn't expect these alpha particles to just essentially be repelled so much that they just bounce back. A good analogy to this is if you have like a bullet, for example, and you point it or you shoot it at a piece of paper, and the bullet hits the paper and it comes right back at you. That's analogous to what's going on here. So, it was very eye-opening just to observe the alpha particles be essentially, repelled back to where they came from. But it was very important because what it told them was that even though it didn't happen a lot, it did happen. And it suggested then, it gave them an idea of what the atom actually was made up of and the components of the atom where they were actually found. So based on this, Rutherford proposed a new model now, not the plum pudding model, but something called a nuclear model, where if you can imagine an atom being spherical, he proposed that at the very center of the atom is a region called the nucleus. And this nucleus is positive. And this is why when they bombarded these atoms, these gold atoms in this case, with the positive alpha particles, most of them went right through. Okay, it's mostly empty space, went right through the atom. Occasionally, these alpha particles would come close to the nucleus, and they're positive charge, remember? So when they come close to something that's also positively charged, they would be deflected away instead of going all the way through. And occasionally, some of these particles, if they were pointed directly at the positive nucleus, they would bounce right back to where they came from. Right? Again, like charges repelling. So this didn't happen very often, but it did happen. And that suggested then that this tiny region in the nucleus had a positive charge associated with it. And that's where all that positive charge is concentrated. All of it is found in that nucleus. So the nucleus then accounts actually for most of the atom's mass found in the nucleus. So it's very, very, very dense. So lots of mass in a small volume. Okay, and if you remember, density is mass over volume. So if your numerator here is large and your denominator is small, this number is going to be gigantic, right? So the nucleus itself in an atom is incredibly dense. So the nucleus itself, very, very, very tiny compared to the size of the atom as a whole. And again, the atom itself is also very tiny, right? So you think about an atom, typical atom radius is about 100 picometers, and a picometer is about 10 to the, not about, but it is 10 to the negative 12 meters. So that's incredibly small, but a nucleus itself is about 0.005 picometers. So if you can imagine sort of an analogy here, if you have like a, maybe a stadium, right? So let's say, imagine this is a AT&T Stadium in Dallas, for example, where the Cowboys play. So we'll say Cowboys Stadium. If you can think of that shell as being the shell of the confines of an atom, the nucleus would be like an M&M at the middle of that, at the very center of that stadium, right? So that's analogous to the M&M here would be the nucleus, and the stadium itself would be the size of the atom. That's how small it is in comparison. So within that nucleus itself, Rutherford and his friends figured out that that nucleus is positively charged. However, whatever that positive charge is, with which they designated the particle responsible for that positive charge was called a proton. The protons and the electrons that they discovered earlier, they did not account. They could not account for all the total mass of an atom. So what they actually found, and specifically James Chadwick, was able to identify the third subatomic particle that's found in atoms, which is also in the nucleus, along with the protons, and that's called the neutrons. So neutrons are, as the name kind of suggests, they're neutral. They don't have a positive or negative charge. They're neutral, but they also make up a significant portion of the mass of the atom. So Chadwick helped, contributed to the body of knowledge of the anatomy of an atom by discovering the neutron. Rutherford, Geiger, and Marsden helped figure out that there's protons in the nucleus as well. These are positively charged. And then we saw that um, Thomson and Millikan helped figure out some of the characteristics of the electron. So those are the three subatomic particles. And in terms of where they are located in a particular atom, so we just said that the nucleus at the very center is our model of the atom. The nucleus holds both the protons and the neutrons. Okay, so I'm going to add this to our table down here. Protons and neutrons are found in the nucleus, whereas the electrons are outside of the nucleus. And some other characteristics of these, we talked about the mass of an electron and the charge of an electron as well. Well, the proton being positively charged has the same charge but opposite sign, right? So instead of being negatively charged, it's positively charged. We assign it a charge of +1, and an electron has a charge of -1. In terms of the masses now, the protons and the neutrons have roughly the same mass associated with them, whereas the electron has a much smaller mass, right? Negligible compared to the mass of the proton and the neutron. So when it comes to this tiny, tiny scale, we use a different measuring unit for the masses of tiny things. It's called the AMU, or the atomic mass unit. And it has an equality in the gram scale. We won't talk about that right now. But in terms of AMUs, a proton is about 1 AMU. A neutron is about the same as well, about 1 AMU. And an electron is way smaller than that in terms of mass. So small, in fact, we can consider it negligible or close to 0. So if you want to calculate the mass of an atom, this is what you focus on, the protons and the neutrons, right? They make up the majority of the mass. And where are they found? In the nucleus. So what does that tell you? The majority of the mass is in the nucleus of the atom, protons and neutrons.